Okay, now we're going to switch gears a little bit and talk about computation in memory. This is also actually a sub-agenda of computation in memory. We've already talked about trends. We've already motivated intelligent memory controllers from the bottom up. Basically, I think there's a push from circuits and devices that require, in my opinion, us to be more intelligent in terms of how we handle memory. So we're kind of pushed from the bottom up. I believe we're also being pushed from top down. The systems and applications are demanding us to be more intelligent with memory. So computation in memory is an old idea, actually. It's not a new idea. The first, in the general purpose domain, the first ideas were developed in the 1960s. Harold Stone has a paper called A Logic in Memory Computer. It was published in IEEE Transactions on Computers, which essentially talks about computation in memory. And it basically gives very good arguments in terms of why computation should be done close to the data inside the memory. And that idea was rehashed many times in different ways over the course of 50 plus years, clearly. It never materialized. I believe one of the reasons is we were never as constrained from both sides. So if you want to, because it's really changing the paradigm, right? Computation and memory are decoupled for a long time. If you want to change the paradigm, there needs to be a really good reason for it. In my opinion, we're at a point where we have all the reasons, meaning we're kind of squeezed in the middle. Circuits are requiring us to do some computation or deal with memory more intelligently because we are having all these reliability, security, and safety issues. And we want to improve performance and efficiency. We also want to be more intelligent in terms of how we handle refresh and other characteristics. And also systems and applications are requiring us to be more intelligent in terms of stuff we put into the memory controllers and memory. And I'm going to motivate this top-down part. I've already motivated some of that, actually. So basically, if you look at the systems, there are three key system trends. Data access is a major bottleneck, energy consumption is a key limiter, and data moment energy dominates compute. We actually showed all of this earlier, so I'm going to go through this relatively quickly. And this data moment energy is especially large for off-chip to on-chip data moment. So the observation opportunity is this. High latency and high energy is actually caused by data movement. We have long energy-hungry interconnects, energy-hungry electrical interfaces, and movement of large amounts of data across the system. The opportunity is to minimize the data movement by performing computation directly where the data resides, or directly near where the data resides. Today, we have no choice. We have to bring the data into the compute unit, which is far away. We have a register file close to it. The register file doesn't do any computation. You need to bring the data from the register file into the compute unit. We have a cache, a lot of data, more data. Cache doesn't do anything. You need to bring the data from the cache into the register file to do something useful. And then you keep going into the hierarchy. You have a huge L3 cache, L4 cache, whatever you have. You still need to move the data all the way from the L3 cache into the compute unit and back. Right? And you go to memory, it becomes even worse, of course, right? Then you go to storage, it becomes even worse. Basically, it's the same story across the memory hierarchy. None of the memory hierarchy components is intelligent. They cannot operate on the small or big amounts of data that they have. As a result, you have large amounts of data movement. So with this perspective in mind, I'm going to use all of these interchangeably. Processing in-memory computational processing, near data processing. I don't care where it happens, as long as it happens close to data. Does it happen inside the memory cell? Does it happen inside the controller next to the data? Of course, you can make those distinctions in the approaches, but overall the approach is really moving computation to the data itself. Okay. So I think general concept is applicable to any data storage and movement unit in the end. Caches, SSDs, main memory, network, and controllers. I'm going to focus a lot on main memory and controllers here. But I think we will need to enable computation across all of these different units that store and move data. Okay, so let me actually motivate in a different perspective. We're going to go back to our friend Maslow here. So our friend Maslow, in the end, didn't say security and safety is the most important issue. The thing he said was, first, you have to have your physiological needs satisfied. You have to have food to live. Because if you don't have food to live, you don't care about your security probably, right? Or you could consider having food to live as a security thing. So energy is probably more important. And I would probably add sustainability over here. Because we have a problem if we don't live. We don't care about our security if the world is going to end soon, right? Okay, anyway. So from my perspective, we want a world that looks like this. Beautiful Switzerland here. Or a world that looks like this, 1940s Pittsburgh. I'm not sure. I think, clearly I want something like this, right? But I also want the productivity of something like this, right? I don't want the bad things here. I want the good things here. So basically, we want everything in the end. We want high performance, efficiency, and sustainability all at the same time. The question is, how do we get there? Well, okay, that's not good. What is the problem? Data access is the major performance energy bottleneck today. And if we want to get to all of those at the same time, I think we need to realize that our current design principles cause great energy waste. Basically, we're moving data all around at the macro scale and at the micro scale. These design principles are causing great performance loss as well. But I put this in parentheses because we try extremely hard to minimize that performance loss or tolerate that performance loss. We know that data movement is expensive in terms of energy and performance. We may not do a lot in terms of energy, but for performance part, we try to do a lot. Meaning we design all of these techniques, prefetching, multi-threading, out-of-order execution, what else did I miss? Caching, of course. Levels and levels and levels and levels and levels of caching everywhere to tolerate that performance loss. And when they work, yes, they may be energy efficient also, in addition to fixing the performance. But when they don't work, or they somewhat work, they actually cause even more energy waste. If you're doing completely random accesses, for example, all of that caching is useless. If you're doing dependent memory access, all of that out-of-order execution is useless. In the end, they actually add a lot more to the energy waste. So we're in this vicious cycle right now to tolerate that performance loss because data, compute, and memory are decoupled from each other. We add a lot of these techniques that increase the energy waste in the system. So we keep doing this vicious cycle. And to basically, if we want to break this vicious cycle, I think we need to really change the paradigm and do the processing of data close to the data. Basically, the problem is processing of data is performed far away from the data. I should also mention that this doesn't have complexity, but the way we tolerate performance loss in existing systems is by adding a lot more complexity into the system, and that increases the energy waste. So if you actually, in the end, have a different paradigm, maybe you have a much simpler system overall, and that simpler system will be energy efficient and also perhaps higher performance because you would get performance by doing something else in that system, right? You can have a lot higher parallelism, for example, in that system. That's used for not tolerating memory latency. That's used for getting parallelism inside the applications. Okay, so this is the problem, basically. Processing of data is performed far away from the data. And again, if you go back to the fundamentals of computers, we need to have three components: computation, communication, and storage and memory. And over the course of decades and decades, we've heavily optimized the computing unit because we've been very processor-centric. All data is processed in the processor. And when I say processor, accelerators are also the same. All of the accelerators that we have are here. They have a decoupled architecture from the memory. And as a result, processor is heavily optimized. It's considered the master, and data storage units have been dumb, and they're largely unoptimized. It says except for some that are on the processor die, but I should fix it. Even the ones that are on the processor die, they're optimized for dealing with the data that's housed, but they're not optimized to do computation, basically. Register files cannot do computation, for example, but you could, I think, do that. Okay, yet we know this. I think I'm not going to repeat this. Yet we have performance is a big issue. We're stalling, waiting for memory most of the time. Actually, more than 60% of the time, according to Google. And this is because we have a grossly imbalanced system. So if actually, when I teach in my first class, I talk about architecture design principles, and balanced design is one of the principles. And we're breaking that principle right away, immediately, in the design of any computer that we have in the world today. So basically, we have a hugely imbalanced system. Processing is done in only one place. Everything else just stores and moves data. As a result, data moves a lot. And this leads to energy inefficient, low performance, and complexity. And as a result, we bloat and make the processor and the accelerators overly complex to tolerate data access from memory. So we have complex hierarchies and mechanisms. Even if you look at GPUs, for example, I don't believe GPUs require all of these massive amounts of multi-threading or huge register files. They're not there to support the parallelism. They're there to support the memory latency tolerance. Some of it is there to support the parallelism, of course, but you don't need huge register files just for parallelism. Okay, so this leads to energy inefficiency, low performance, and complexity. So as a result, we have the picture that I showed you earlier. Most of the system, more than 90% of the system, is dedicated to storing and moving data. So I've already given you the energy perspective also. I've already said this. Let me tell you one more thing over here. So this is, let's say, today-ish. If you go back 70 years, the cost of this logic operation was actually about 2 orders of magnitude more than the cost of a memory access at that time. Of course, you cannot get exact numbers 70 years ago because people were not as concerned with energy, but if you extrapolate, basically we moved 5 orders of magnitude to the other side, meaning memory became much worse. But we're still designing the systems to move the data into the processor. And again, this is obvious in the sense that with technology scaling, logic scales, but interconnect doesn't scale as much. As a result, you move 5 orders of magnitude because logic scaled really well. And logic keeps scaling still, right? People are going to 7 nanometers right now. They're already at 7 nanometers, actually. Okay, I'm going to skip this because I already said that. It costs about 100 to 1,000x to move the data compared to doing a sophisticated computation operation. As a result, you have pictures like this in real workload. More than 60% of the entire system energy is spent on data movement. Basically, I think we do not want to move data. In the end, processing in memory, near data processing, whatever you call it, it's really a data movement problem. We're moving data too much. We do not want to move data at all. If the caches were extremely effective, maybe that was a good idea, right? If you have perfect locality, then you're not moving data also. So that could be a good solution. If you have very good locality, caches are a good solution, actually. But in many systems that we have today, caches are not that effective. So why are people building large caches? Because it's the easy thing to do, right? You can always add more cache. And there are some workloads that benefit from more cache, no question about that. Okay, so basically we need a paradigm shift to minimize data movement, enable computation with minimal data movement. I call it computing where it makes sense, where data resides, which means that we should have the ability to compute wherever the data resides. And this, I think, is a more data-centric view of the world. We should make computing architectures more data-centric as opposed to processor-centric. So we're going to look at processing inside memory. This is one example of where data resides. And I think it's a very special example of where data resides. Clearly, storage is another place, which is very interesting. Caches are another place. I think memory is interesting because it is becoming bigger and it has a lot of data in it. And maybe doing this inside the memory is harder than other places because today we don't have the interfaces for it. And we also have a huge partitioning across the industry and businesses in terms of compute businesses and memory businesses. Even if you look at a company like Samsung, who I believe is the best place to actually do something like processing in memory, they are partitioned in terms of the compute business and memory business. They don't talk to each other. There's an SoC business that designs the cell phones. There's a memory business that designs memory, and they don't talk to each other. I believe they're missing a huge opportunity, but anyway, I'm not making their money. Okay, so basically, I don't know what happened here, a bit flip. What we would like to do is we'd like to store interesting data, and we have a lot of interesting data that's growing in memory, and we'd like to be able to talk to memory from some unit. It doesn't need to be the processor, it can be the accelerator. It could be anybody who wants to do something on that data. And we want to query that data, and the memory, we want to ask questions actually, not just queries. We can ask questions to the memory. Memory, can you do this operation for me? If the memory is capable, it's going to do it, and they're going to send you some results, and then you can do handshake and do partitioning of the work so that you can do better. So there are clearly many questions over here. How do you design the compute-capable memory and the controllers? How do you design the processor chip and the in-memory units or the accelerators after this happens? Because if this happens, maybe you don't need very capable or very sophisticated processor chips. How do you design the software and hardware interfaces? We don't have any of those today. Because actually the interface between processor and memory is really, I don't want to call it simple, but not sophisticated. It assumes that memory is dumb, basically. You cannot do anything. You can read from memory, write to memory, you can refresh memory, you can do some power management, but that's it, basically. You cannot ask intelligent questions to memory. On top of this, of course, how do you design system software compilers and languages and the programming models? And on top of this, I think, how do you design the algorithms and theoretical foundations? I like thinking about this because all of you are computer scientists, probably, or electrical engineers. At some point, you've taken a theory of computing course. And in theory of computing course, when you analyze the complexity of algorithms, you count operations, right? You basically have the big O notation. It counts how many times you do an operation. This tells you nothing about the data movement cost, right? In a sense, we've been optimizing our algorithms in a processor-centric manner without thinking too much about it. This is because of the way things are designed. All of the theory has been developed for processor-centric designs. Whereas if you're data-centric, maybe there are different ways of analyzing algorithms. And I think there should be different ways of analyzing algorithms. So I think this actually cuts across even into the theory of computing, basically. All of the things get disrupted. And clearly, I'm not going to answer all of these questions for you, but I'm going to tell you that this is really exciting in the sense that it really cuts across the stack. There are things to do everywhere. And I think if you really want to take advantage of it, you really want to think co-design across the stack. And I'm going to show you with some evidence from our work that if you do things without thinking across the stack, you're not going to get a lot of benefit. You're going to get the most benefit if you actually co-design across the stack. Okay. So just to finish up the motivation over here, basically we have a huge push from technology today. People are actually interested in controllers close to DRAM. Industry is open to new memory architectures. They've been designing 3D stacked architectures where you can put logic that's relatively tightly coupled with memory with high bandwidth and low latency connections. Actually, Micron has interesting designs that do some deterministic finite automata computation inside the row buffers. Very limited functionality, but they've actually done it. And there's a huge pull from systems and applications that I'm motivated right now. And actually, things are happening. I think there are multiple startups that are doing this. This is one example. This is the UPMEM or UPMEM, how they call it. They actually went and put some compute units inside the DRAM chip and associated with each bank. Now, there are, of course, limitations over here, but there are people who are really designing this. I think this comes at high cost compared to what we're going to describe in a little bit. But there are startups that are working on it. I think these folks are actually relatively close here in Grenoble. Yeah. Okay. So things are actually moving forward. It's very different from the landscape that is there in 1960s, 70s, 80s, 90s, 2000s, and 2010s. We are actually having people look into, and people are actually thinking about commercializing this. We'll see if it happens, of course. And we can talk about that also. But I think given that, we still need to think differently from past approaches. Basically, a lot of past approaches were, let's put a vector unit inside, let's put a processor inside DRAM. Or let's put some vector unit inside DRAM. I think that's not going to be very easy. Although UPMEM approach is interesting because they're not putting a full-blown, sophisticated processor. They're putting a simple processor over there. But if putting a very sophisticated processor, DRAM and processor fabrication is very different from each other. Logic and memory is very different from each other. So having a very good processor inside the DRAM is not going to be very easy. Now, if you do 3D stacking, it becomes easier because now you can optimize this layer for logic and optimize this layer for memory and connect them. And people are actually looking into that. So that's going to be easier. That's why I say we need to think differently from past approaches. So let's talk about thinking differently. I'm going to talk about two different approaches today. One is minimally changing memory chips. And I think this is very interesting. Surprisingly, not many people have thought about it for a long time. Maybe because the mindset was not there. And I think these are both applicable to non-volatile memory, emerging memory technologies also. And in fact, emerging memory technologies are going to be even more capable because perhaps you're going to be able to do more than minimally changing memory chips over there. Okay, let's talk about the first one. So what does minimally changing memory mean? Basically, any type of memory, DRAM is a specific case, it has great capability to perform bulk data movement and computation internally with small changes. You can exploit internal connectivity to move data. You can exploit analog computation capability inside the memory. And this is true for non-volatile memories as well. And you can, of course, add more. You can add more internal connectivity to move data within the chip. You can add more to do more computation, analog and logic. But if you keep adding more, the cost increases. But there's some natural computation capability that's already there. And we'll talk about that. I'm going to give you some examples. And I'm going to start with something simple. Something simple meaning I'm going to cheat. This is not even computation. This is data movement. This is essentially data copy and initialization. But that's the cause of data movement also in the end. So bulk data copy and bulk data initialization are useful things. Imagine you're initializing a huge database, right? 1 terabyte. You set everything to zeros or whatever value you want. It takes time, basically. It takes energy. And clearly, data copy and initialization is useful in many, many things. I'm not going to talk about that in detail. Actually, whenever it's really performance critical, what people do is they refactor and redesign their software to minimize the data copy. And whenever they do that, the software becomes more complex and even hard to read. And it becomes very hard to maintain. So that becomes a problem. So if you actually have a copy operation that's extremely fast, maybe you can actually make the software design much simpler as well. So you can change the algorithms. So actually, this Google paper, which I mentioned earlier, they show that just these two system calls, memmove and memcopy, occupy 5% of the execution cycles across all of the workloads that they've studied in their data center. And according to them, this is all of their data center workloads. I think it's fascinating to see just 2 system calls being responsible for 5% of the execution cycles. They call it as part of the data center tax. And actually, they reference the work that I'm going to describe next as one way of alleviating this data center tax that's due to these system calls or data movement because of that. Okay, so we're going to talk about bulk data copy, and within a node, of course. So the basic idea is, how do we copy the source page to this destination page? Let's assume that's 4 kilobytes. Of course, the problem becomes bigger if this is 1 megabyte or even larger, right? So basically, in today's systems, you need to bring the data all the way into the CPU. In the worst case, you bring the data all the way into the L1 cache, right? And then bring the destination page in the L1 cache, do the copy, and write back the destination page in the destination. Of course, you can set up the DMA controller, direct memory access controller, to do that operation for you. It takes some time to set up, but then at least you don't pollute the caches, right? So you have the option to do that, but regardless, you exercise this huge interconnect. So this is high latency because you have to go through that. This is high bandwidth utilization, perhaps in the most important component where you should really save bandwidth. This causes cache pollution, but you could eliminate that by doing this through the memory controller or DMA engine. This causes a lot of unwanted data movement. Imagine you're really initializing. Actually, initialization is a special case of copy, right? If you want to initialize 10,000 pages to 0, you can initialize 1 page to 0 and copy that page to the remaining pages. So basically, this causes a lot of unwanted data movement. Or even if you're doing the copy, you may not actually use the page immediately, right? The destination page. So if you actually do this copy through the direct memory access engine, not even going through the cache hierarchy, for a 4 kilobyte page, in DDR3 technology, it's about 1,000 nanoseconds and 3.6 microjoules. DDR4 doesn't improve that. We're going to talk about latency. Going from DDR3 to DDR4, some of the latencies actually increase. So you don't get better performance. And that's part of the problem, actually. If you're actually thinking about replacing your DDR3 with DDR4, you better have a good reason. Okay, so if you actually show this picture to a 10-year-old child and said, look, I'm doing this, can I optimize my system in a better way? Sometimes we should probably think like children. And maybe the child will tell you, why don't you just do it like this? Isn't it much more simple, right? And I think that's the idea, basically. Hopefully the idea is obvious. We do it inside the memory without disturbing anything else in the system. This is low latency. This is low bandwidth utilization. There's no cache pollution here, but you could eliminate that today. And there's no unwanted data movement. So I'm going to show you a mechanism that takes us 1,000 nanoseconds to 90 nanoseconds and 3.6 microjoules to 0.04 microjoules. And if you optimize it, you could actually do better. I'm talking about the unoptimized mechanism. And the idea is called row clone. It's a very simple idea, at least within the DRAM subarray. So DRAM consists of subarrays. We've seen the subarray earlier when we talked about row hammer. Basically, imagine that each row is 4 kilobytes, and they're connected to the row buffer. What we're going to do is, if you want to copy a source row to a destination row, we're going to use this row buffer that already exists in DRAM as an intermediate place. The idea is very simple. You first activate the source row, which connects the source row of data to the row buffer. Now the data gets captured over here reliably. The next step is another activate. But now you activate the destination row, which implicitly deactivates the source row, but its data remains intact over here. And once you activate this one, the row buffer gets connected to the destination row, and it basically transfers its data into the destination row. This happens because the transistors over here are much larger and much stronger. In fact, the size of a DRAM cell is, the size of a single row buffer entry is more than 100 times the size of a DRAM cell, because this is really the sense amplifier. Yes?
What is the consistency of these operations?
What do you mean? You mean coherence? So here, the coherence, somebody else needs to deal with it. And that's in general a problem with processing in memory. Whenever you're doing processing on the data inside DRAM, if you have some part of this data in your processor caches, you should have flushed it out, or you have a good idea of what you're doing with it.
How about crashes?
What do you mean?
Something breaks in between. Doing those transfer now,
Uh-huh.
then something can happen in there, and then what are the...
But that happens in existing DRAM also. This is volatile data. So that could happen whenever you're reading from memory today also, right? inside when you're going through the processor. So it's the same issue, basically. You need to have higher level mechanisms to tolerate those things. No question about that. But I think those mechanisms are not that different from existing mechanisms, with the exception of coherence. Coherence needs to be carefully thought because now you have another place where you need to worry about coherence. Yes?
You're orchestrating those moves through the controller.
Mm-hmm. Controller basically says copy this row to the memory. That's it. Yeah. You basically, data doesn't go inside the controller.
And this is standard interface today?
So this is actually very interesting. We're going to talk about that in a little bit. So what we said, proposed in this paper is you need to have 2 consecutive activates, and you could do this with standard interface, but it requires simple changes to DRAM. So you need very simple changes. Okay, maybe I'll tell you. So this was published in 2013. Somebody else in 2019 used our SoftMC infrastructure, and they showed that you could do this in off-the-shelf DRAM chips by modifying the timing parameters in your controller. So with existing interface, you could do this reliably. So I'm going to have a story about that later on. So this is actually very easy to do. And we always argue that this is really easy to do. But to be able to do it reliably without messing with timing parameters, I think you need to do this 2 consecutive activates. And you need to have very simple logic. Yeah.
My understanding is you can do this with Flash, and there's a standard ways of doing this independent of the Flash, the packages that you're using.
Mm-hmm. In DRAM, there's no way, yeah. In DRAM, basically, they don't allow you to do this unless you mess with timing parameters, which if you actually go and tell the manufacturers you mess with timing parameters, they will basically not talk to you because you're basically violating the standard. So if you get any errors after that point, it's your problem. So it's not part of the interface. Yeah. So it's very easy, basically. Flash is a bit different. In Flash, the data movement is a little bit different. But yes, you could do it in Flash also.
I think they have higher standards than this. Non-Flash standards.
Yeah, exactly. Some of those standards are there. In DRAM, there is no such interface, for sure. Yeah, we need to move to some interfaces that are much more flexible, for sure.
Just as a side, are the manufacturers the same?
Oh, so this, you mean in terms of how this operates?
The manufacturers that accept on-file are the same that do not accept the standard here or no?
So that's a good question. Yeah, I mean, we can talk about that, yeah. Okay, so the basic idea is 2 consecutive activates is negligible hardware cost. And this gives you more than 11x reduction in latency and 74x reduction in memory energy. This is not the entire system energy, it's just the memory energy for moving this 4 kilobyte copy. So of course, this is not enough, right? This is just a subarray. Although, if you want to maximize your benefits, you really want to move your page. If you want to do a page copy, usually the way page copies are done today is on copy on write, right? And whenever you want to do a copy on write, if you really want to maximize the speed of your copy, your operating system should really allocate the destination page in the same subarray. But of course, today we have no idea about where a page is allocated at the operating system level. So we really need to understand the structure of the DRAM better if you want to maximize the benefits of it at the higher levels of the system stack. No question about that. But there are cases sometimes you may want to move data from one bank to another. And that actually can happen also through the shared internal bus. For example, if you want to move even a byte from this page here to this page here, you can basically go through the shared internal data bus. Memory controller, again, orchestrates this, so that the data doesn't come out of the memory controller. And we introduce some commands for this. This requires some commands that doesn't exist in DRAM. So, and of course, if you do this for a given page latency, so page copy latency reduces by 1.9x and energy reduces by 3.2x. So clearly, you're moving data more this way. That's why the reductions are lower. But this has the advantage that your granularity can be anywhere from a byte to a page in this case. Whereas in the previous case, the granularity is always the raw granularity. So that's also another thing that is to be, that we should be cognizant about. The data mapping becomes important because you're dealing with structures that are very close to hardware, and the operations are done at the granularity of those structures. And if the granularity of the operation that you're doing in software doesn't match the granularity of the structures, you need to somehow program it nicely and map your data nicely such that you get the benefits. So that's part of the adoption and programming issues that we were briefly talking about earlier. So there's also the generalized row clone, actually. Intra-subarray is very simple, very fast. Interbank is, as we discussed. The hardest part is really this inter-subarray. It turns out within a bank in memory, across different subarrays, the same subarray shares row buffer over here, but the different subarrays share essentially no row buffer. So you have to actually go to some other bank and copy the data from that bank back into the subarray. Although we developed some solutions by changing the DRAM microarchitecture that actually makes it much better, that I'm not going to talk about now. Okay, so the overall area cost is actually very, very simple over here. And these are the different benefits that you get from interbank, or intra-subarray, interbank, and inter-subarray. You can see that if you actually are moving data from one subarray to another subarray, you don't get latency benefits, but you still get energy benefits because you're not moving the data out of the chip. But our later work actually reduces that this to over here somewhere. Okay. Okay, if you're interested, you can read this paper. I would also recommend reading the Micro 2019 paper by the Princeton folks that I'm going to reference. So, okay, I think the mindset that we have over here is thinking about memory as an accelerator. Basically, we're building all of these accelerators, and they're all good at what they do, but they're all sitting on the left side of the memory bus over here. Why don't we have something on the right side of the memory bus that is designed to take advantage of what memory is really good at doing? And memory is really good at doing this sort of data movement that I just described. It's a very specialized mechanism, but whenever you invoke it, you get a lot of benefit. So, and I think you'll have all kinds of similar programming issues that you have from these accelerators also. So you need to deal with coherence whenever you move data between these. You need to deal with other issues, programming benefits. You need to make sure your data is partitioned nicely between the accelerators. Again, we're going to talk about that, yes.
Before you move on.
Sure.
So you're just supporting memory moves here, and you have a strong reduction in the energy cost.
Yes.
But this is a discussion we had already before. You still need at some point to trigger the cache coherence protocol because
yes.
And you don't account for that in the measure of energy.
So that is correct. I don't account for that. The paper has so the results that I've shown you are pure page copy results. The paper has application level results that account for all of that. So you get significant benefits for applications that do page copy. It's not going to be 74x, of course, but you get significant benefits. Yeah. So system level results definitely need to take that into account for sure. Yeah, absolutely. Exactly. It has some cost, and somebody needs to do the data mapping to make it work, right? Because if your row size doesn't match the granularity of the data movement that you do.
Memory model, we need some. It's like the alpha processor. We need some more memory barriers, some crazy things.
Exactly. Yeah, you need to handle. Actually, it's not that bad. I'm going to talk about some of the simple programming methods. Yeah. Alpha may be bad, but yes. I think basically designing programming models to take advantage of this is an open research problem. No question about that, and we should get it right. Okay, so I'm going to talk now. I've kind of cheated. I talked about copy. I've said that initialization is a special case of copy. Actually, initialization is even easier because you just write data to an entire row. You may actually, their coherence becomes easier. And the benefits, if I remember correctly, are you basically reduce the latency by 6x and reduce the energy by about 42x in terms of 4 kilobyte page initialization. But we can support even more, bitwise and, or, not, and majority at low cost. I'm going to give you the ideas. And we're going to use the analog computation capability of DRAM. I know this is going to be very low level for many of you, but let's go into it. Basically, we're going to activate multiple rows. And it turns out activating multiple rows concurrently performs computation because of the charge sharing nature of DRAM. And I'm going to show you some performance results, and we're going to look at that paper. But before I go into that, new memory technologies are all capable of something like this, actually. I'm going to reference a paper later on also that came out after our paper. But basically, memristors, resistor RAM, phase change memory, SCTM RAM, they're all capable of some sort of analog computation. In fact, more than DRAM, they can, because of the cross-point structure of memory or two-dimensional structure of memory, you can actually do matrix multiplication, for example. You can actually operate these memories in a systolic fashion. And I think it's very interesting to think about that. But I'm not going to talk about that. And the benefits are going to be even higher because in DRAM, fundamentally, whenever you activate a row, you're fundamentally destroying that row in DRAM. A read is destructive. Whereas in these technologies, reads are not destructive. So you can actually get away without moving data, assuming your algorithms allow it, of course. Okay, so what's the basic idea for computation in DRAM without adding computational logic? The idea is very simple. You have these 3 rows. I'm showing you only 1 bit from each row, the capacitors and the bit line, and this is the sense amplifier. Imagine this being 8 kilobytes. That's in one subarray. And imagine a DRAM chip having, let's say, 5,000 or 10,000 subarrays. If you multiply 8 kilobytes with 10,000 subarrays, that's a big number. Basically, you can do this operation on a lot of bits concurrently. Of course, the caveat is you need to increase the power budget to your DRAM chip, because DRAM is not designed that way, designed for that purpose. And you need to probably put a heatsink on your DRAM, because now you're doing computation, right? I'm saying this because sometimes people want zero cost in everything else when they're getting 80 million bits per operation, right? That doesn't happen. There is no free lunch. You will need to pay the power cost and the cost to cool this down. Okay, so what's the idea? Basically, if you concurrently activate these 3 rows, you connect the capacitors concurrently to the bit line. And what happens is, because of charge sharing principles, if at least two of these cells are discharged, you get the charged, you get the charge state at the end. If at least 2 of them are discharged, you get the discharge state at the end. And that's a majority function. Basically, you get the bitwise majority of these 3 cells, which is very interesting by itself, right? Because you can actually now do bitwise majority computation on 80 million cells or whatever. And I think bitwise majority is very interesting. If you read Donald Knuth's 4th book, he talks about bitwise majority as being a very beautiful function. And there's work at EPFL actually that Nani does, that where they actually convert the logic synthesis into many, many bitwise majority operations that I think would map nicely here also. I mean, this is a nice function by itself, but actually the next realization is very simple. If you rewrite this Boolean equation, now you can control C. If you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. Now you get a bitwise OR and bitwise AND, which is nice. But it's not functionally complete. It's not Boolean complete. So we want to add a NOT also. But before we go into that, basically, how do you expose it to the higher levels? This is one way of exposing it. I'm not saying that this is the best way. But you can add an operation like bulk AND, row A, row B, row C, or page A, page B, page B. Some granularity needs to be defined over there, or it could be configurable. And this performs a bitwise AND of 2 rows A and B and stores the result into C. So how do we implement it internally? Basically, I'm not going to go into the circuit level details too much, but if you allow this triple row activation in all possible rows that you have in DRAM, you're in for trouble, because that's going to be a nightmare to implement. That's a bad decoder. So we actually have a special area in each subarray where you need to move the rows to do this triple row activation, and only those rows are capable of triple row activation. So those are the designated rows. And we also reserve 1 row for 0. We reserve 1 row for 1, so that you can do AND or OR. So the way we do this AND is, so you have a row A, you copy it into one of the designated rows using row clone. You have a row B, you copy it into the other designated row. And then you row clone R0, which is all zeros, to row D3, because we're doing AND, and you need to set C to 0. And we do the triple row activation. Now the result is in any of those rows, D1, D2, D3. And you row clone the result back into the array, C. So clearly this doesn't come just like activate, triple row activate. You actually need to do the copies internally. But it turns out doing all of this is much faster if you're dealing with a lot of data in parallel compared to moving all of those bits into the CPU and other places. Okay, so as I said, this is AND and NOT, AND and OR. In order to have NOT, you need a little bit more cost. So unfortunately, if you actually activate a row, the complement of the row exists in the other side of the sense amplifier, but it's not connected to anywhere. So the idea over here is to feed the complement that already exists into some special row that we add to DRAM. Again, we don't need to add any logic, because the logic to the complement already exists because of the sensing structures, but we need to add another row to capture that value. That's the idea. And this adds a little bit more cost into DRAM. But now you can do anything in DRAM, because it's Boolean complete now. You can do AND, NOT, and OR. Now, the beauty of some other memory technologies is, for example, memristors, you can do directly NOR. If you have a bitwise NOR, it's very similar to actually this idea in the end. You could map a lot of the applications that we map over here. They can map also. But if you have a bitwise NOR, again, you're Boolean complete. Right? Some other technologies, you can do bitwise NOT and AND as well. Okay, so, yes?
While you're doing this computation, you block the entire array.
So yes, while you're doing the computation, you need to block the entire array. That's right.
You just created 3 registers, and you're kind of coming with instruction sets.
Exactly.
That could be implemented in an analogic fashion.
Exactly. But if you're not doing this operation, you can still use that array as your memory. You can still access it. But while doing it, yes, it's blocked. OK, so what are the benefits? I'm not going to go through this one. I think I'm going to summarize it compared to DDR3. But basically, you get significant performance improvements. So we compare it to some not-so-great GPU. But this is a state-of-the-art hybrid memory cube engine. This is the throughput in gigaops per second. This is 3D stacked memory. And we do much better than 3D stacked memory in the end. Because even 3D stacked memory needs to move the data from the DRAM layers into the logic layer. And that costs energy and performance because you go through a heavy interconnects. If you keep the data inside the DRAM layer, you get much higher performance. OK. And these are the performance improvements and energy reductions. Actually, this is the energy reduction. Basically, for NOT, you get about 60x energy reduction. And/or is a little bit more costly. NAND/NOR, you can build up, of course, 35x. XOR XNOR, you get 25x, ... OK, and that's summarized. So, of course, the next question is, what benefits from it? I believe, actually, by rethinking your algorithms, you can potentially rewrite many, many applications to take advantage of it. Actually, there is a lot of really interesting work that was done in the 1960s on vertical data processing systems. Basically, they basically relay out their data to be vertical, and they want to take advantage of bit serial computation. And this is essentially bitwise computation, right? You can think of it as bit serial computation also. If you want to build an addition on top of this, you basically do bit serial addition. So I think maybe we should really revisit the way we design algorithms if you really want to take advantage of something like this. And I believe this can be a general purpose substrate once you do that. Of course, I think this is a more general purpose substrate if you couple this together with a 3D stacked logic layer where you can do more complicated operations in the logic layer. For example, if you want to count bits, it's probably a good idea to do that in the logic layer underneath. But some algorithms, I think, are even better fit over here, like bitmap indices that are used in databases. Some people have designed databases, like the bit-weaving database from Jignesh Patel's group. They designed it to maximize the bitwise operations. And we actually ported that database, or parts of it at least, to take advantage of mbits, and we see significant benefits. Microsoft has also rewritten their web search engine to actually, in a very similar manner, to take advantage of GPUs to maximize the bitwise operations. DNA sequence mapping actually is very bitwise operations, encryption algorithms, a bunch of other things. I'm going to show you some high-level simulation results because this doesn't exist clearly. I'm going to skip this. Clearly, bitmap indices. Many people know bitmap indices. You basically do a lot of operations on bitmaps as opposed to other types of representations. OK, so we basically map bitmap indices and some queries using these bitmap indices on mbit, and we see significant performance improvements. Basically, as your data set size grows, actually performance improvements also grow because you can parallelize across different subarrays. And this is about 5 to 6x, as you can see over here. This is the bit-weaving database. We mapped that also onto mbit. And again, we see this database is designed for maximizing bitwise operations. And again, we see significant performance improvements. So, of course, this depends on the query, but this is on one query. You get significant performance improvements. Again, as the data set size grows, the performance improvement also grows. So we're scalable as long as you remain on the same chip, of course, in DRAM. OK, so if you're interested, you can. This is our original paper where we didn't have the NOT. We had the AND and OR, and we didn't have all of the application level evaluations. But this is where we actually added the NOT also, now that we're Boolean complete. And we have actually a recent invited paper that talks about this in DRAM bulk bitwise execution engine. And if you really want, I'm very proud of the DRAM background that we wrote over here on section 2. If you really want to know about DRAM, I would recommend section 2 over here. Yes, please.
I'm trying to think loud. So there must be some problems where the bitwise algorithm that you use becomes quite complex. I mean, there's a long sequence of operations.
Absolutely, yeah.
There's threshold after which it's better to move the memory to the CPU, do the fast stuff there, and then ship it around, rather than having all these instructions that will sort of also add up.
Yeah.
So do you have some rule of thumb for that?
Not yet. We're working on it. We have a paper submission that talks about some of that, but I think I don't have a immediate rule of thumb by looking at the algorithm, because you can always also represent your data in a different way to minimize that, right?
And did you compare the GPU implementations?
So we do have some comparison with GPU implementation, and it does much better than GPU.
And vector SSE?
Yes. We did compare to that. Yes. Sure. Yes.
Just very quick. Again, the premise is you're not changing, you're not touching the circuits. You're not changing the manufacturing process. You're not adding any circuitry to do this calculation.
Well, we're adding circuitry to do the triple row activation, right? But we're not adding circuitry for the, we're not adding an AND gate, for example, or NOT gate. ALU, basically, we're not adding.
The array is the same.
Exactly. The array is, well, we are changing the array so that we can do triple row activation in a part of the array. But the changes to the array are regular. In row clone, we're not changing the array. In this, we're changing the array.
And the limitation is you say in the beginning the manufacturing process to do CPUs and to do memories are very different, and it's very complicated to mix those two in the same.
Yeah.
Is there anything in between? Can you change a little bit the array?
Yeah, absolutely. I think you can actually change the array even more than what we did, but we wanted to exploit this without adding functions. So, for example, if you want to add some accumulator right next to the array or outside the array, I think you can do it. But we've been exploring some of those ideas. Okay. Any questions? Then I'll ask you a question. Okay, I'll skip that one. So basically, I think that we have a huge challenge and opportunity for the future. How do we design computing architectures with a minimal data movement? I don't know if I want to go through the detour on the review process. Some students may be interested in it. Okay, let me go through it. Hold on.
Just count time because we need to finish at the latest at 7, I think.
Oh, okay. Okay, I will still go through this detour on the review process very quickly.
That's the
Yeah, no, we have the resolution.
I see. So maybe I'll finish computation in memory and then we'll leave the rest for some other time. Okay. So let me go through the review process because I think this is instructive and some of the students may be suffering from the review process also. But so MBIT sounds good. No, I think it sounds good actually. It actually sounded good to the reviewers also. So this is one reviewer. You can see the strengths. This is directly copied and pasted. Very clever, novel idea. Great potential speed up and efficiency gains. But weaknesses probably will never be built. Not practical to assume manufacturers would change DRAM this way. I think this is a very bad reason to reject the paper. Because if this is the mindset, you will never enable a new idea, right? You can never build anything new this way. This is a review from ISCA 2016, and this paper did not appear in ISCA 2016. Okay, anyway, another review very similar, basically. It's unlikely that something like, basically everything, the strengths are very strong, but the weaknesses are very speculative, in the sense that, how can you prove this scientifically, right? And on a scientific basis, how do you reject this paper? Anyway, so think about this. Yet another review. I don't like this also, but this is a different kind, basically. I do not find architectural innovation. I'm an architect. I don't care about your work. So don't bother me with your circuits technique, or don't bother me with your operating systems technique. Anyway, so I think this is a very bad mindset going forward. We should really be more accepting of across the board, basically, because as I said, the solutions are not going to be easy at one level. And this, by the way, this is also something that I very disagree with. This is a circuit level technique that you take advantage of a circuit level technique at an architectural level, right? Okay, that's why we acknowledge the reviewers from multiple conferences. So if you get papers rejected, don't worry. It's happening to a lot of people. Okay, but I think more generally, we have a mindset issue. There are many similar examples for many other papers. And actually, I'm not even talking about industry yet, because industry has this body called JEDEC, which defines the DRAM standards. And it's extremely political. I'm not going to go into that. So how do we fix the mindset problem? I think we really need to continue pushing forward and doing research, education, implementation in these alternative processing paradigms. Basically, somehow we need to enable the better future, regardless of this sort of comments. Because these naysayers will always exist, in my opinion. But I think this is very important. We somehow need to fix the reviewer accountability problem. And it's getting much worse, I think, in general. Certainly in computer architecture, but probably also in other areas, because I also send papers to some other areas also and get, for example, well, that was also in computer architecture, but anyway. We had sent a paper to one of the conferences where we studied, let's say, 115 applications and 9 different DRAM types. And we basically wanted to understand which application works better with which DRAM type, and which DRAM type is a good fit for which application. And I think this was actually published in Sigmetrics last year. But we sent it to an architecture conference, and one of the comments we got was nonsensical, in the sense that you didn't do the study in a real system. We did it in simulation, of course. But there's no real system that supports more than one DRAM type, as far as we know, in the same, attached to the same processor. So this is interesting, right? I would love to have that system. I would love to build that system, but actually even building that system costs a lot. Why? Because you really need to have so going from DDR3 and DDR4, first of all, you need to support both. And these have different PHYs. These have different physical interfaces. So you need to pay a lot of cost. Ignore all of the pin costs. You need to pay a lot of cost to actually get that PHY, analog interfaces. Imagine having 9 of these in a single system. So I would love to have it. Anyway, okay. Just like main memory needs intelligent controllers, we need more accountable reviewers, basically. Okay, so having said that, I think it's good to, if you believe in an idea, it's good to push forward. Because row clone was rejected for a similar reason, actually, earlier. I don't talk about that. But this is the paper that I mentioned from Princeton that got published in Micro 2019. And this paper showed that you could actually do row clone on pretty much all of the chips that they've tested by reducing the timing parameters. So what they did was they reduced the timing parameters to imitate consecutive row activations. Now, that's not it. They also showed that basically these are off-the-shelf DRAMs. You just change the memory controller slightly to change the timing parameters. They also showed that in a subset of the DRAM chips that they have tested, you could do these M-bit-like operations. Basically, they were able to show, without changing the DRAM chip, just like we described. I think to be able to do it reliably, you need to change the DRAM chip. But they were able to show that by reducing the timing parameters, they would be able to get the chips to imitate this triple row activation. And in some fraction of the chips, they would get bitwise AND and bitwise OR operation. And they would also show majority, basically. So this is actually, it's very interesting to get this sort of comments that I showed you earlier, when actually it's possible to do it. And basically, based on fundamental principle, it's clearly possible to do it. No question about that. This sort of work that shows that you can actually do it in existing DRAM chips without modifying is very, very interesting also. Now, granted, I think if you really want to do it, I don't think this is the way to do it, because this is not reliable. If you want to make it reliable, you need to really modify the DRAM chip internally. Okay, so you could actually do this in phase change memory also, very similar to what we've described. These folks, actually this paper was published in DAC 2016 after our bitwise operation paper. They showed that you could actually do this and you could accelerate a bunch of applications in phase change memory. So the fundamental principle is really applicable to many different types of memory, in my opinion. Okay, let me share you with some more fun with our Rowhammer reviews. So when we sent the Rowhammer paper to Micro, it got rejected. You can see the reviews over here. This is the overall merit. That's the most important part, I think. So some people really liked it, as you can see, and some people really hated it. So why did they hate it? There's no architectural content. They don't like it. Okay, I don't agree. So basically, they said that it's not really realistic. It doesn't happen in realistic DRAM usage, which I think I know what they mean, but I mean, security is a real DRAM usage, right? Real DRAM exists. You got to be careful about how you secure it. But actually, anecdotally, this happens in some real applications also, which is really sad because it's a very hard bug to find. So some real applications, because they want to do the locking in some way, what they do is they make the lock uncacheable, and now lock is somewhere in memory, and different applications actually hammer memory. And as a result, people have seen that Rowhammer happens in some of these applications, and it becomes a very difficult bug to find. Anyway, you can see the reviews over here, basically. The paper doesn't discuss the root causes, many known disturb mechanisms. I think I don't need to talk about the benefits of the paper. Okay, but I think we sent it to Micro. It got rejected. And later, we sent it to ISCA, where it was published. We still got some reviews that were actually a bit sad, I think, in the sense that they basically pointed us to this YouTube video. So this review says basically it doesn't happen, right? It's not important. And later, some reviewer, I don't know if it's the same reviewer, but they basically point us to the YouTube video that basically says, oh, this is already done, basically. You can even find a YouTube video showing this. Now, I know this YouTube video very well because I was at that conference presenting DRAM scaling. And there was this folk from Teledyne Reclory where they actually showed that they built this circuitry to actually test for the Rowhammer issue. They were not supposed to talk about it, but they did talk about it for about 1 minute or so, or 30 seconds. Now, equating a scientific paper with a 30-second treatment of Rowhammer and marketing is, I think, dismissing science. I had to revise this title over here. And I think a reviewer should not dismiss science. Okay, anyway, this is also interesting. Basically, we send the paper to a conference 6 months earlier, and we get rejected because they don't believe the problem. And 6 months later, it's already a known issue. And that's the reason for rejection. That's very funny. Anyway, this is not to complain, but this is to show that these things happen, and we need to be cognizant about it. But in the end, I think the ISCA paper got accepted, even though these dissenting reviewers had some interesting arguments to make. Yeah, the scale was 8 here, I think. I think the scale for micro was maybe 5 or 6. Here, the scale was 8 or 9. I'm not sure. People play with the scales all the time. I don't know. I think this was award quality or something like that. I don't remember. We can dig it up if you're interested. Yeah. Okay, so this is actually what I presented in ISCA this year. Suggestions to the reviewers. Maybe I was too bold to say these, but I think this is really important, basically. In the end, we do not know it all, right? We're scientists, and we're dealing with something we do not perfectly know, and this is a snapshot in history. So we need to be really fair and open-minded. And diverse research methods is really important because I think if you're doing research across the stack, you may be suffering from this also. Anyway, okay, you can read this on your own. So I think in the end, the downside is scientific progress gets delayed or blocked for non-reasons. And I have a lot of stories. Whenever my students get some rejection on a paper that they really believe in and they get upset, I point them to these papers that were rejected from major places, and later they went on to win Nobel Prizes. If you look at those papers, they were not published in top places. Okay. So for researchers, I think I would recommend following your passion. Do not get derailed. Take the best out of the reviews, but ignore the maybe not so interesting parts. Be resilient and focus on learning and scholarship. In the end, the quality of your work defines your impact. And so I have some more thoughts and suggestions on this if you're interested in looking at. Okay, maybe I'll talk about this paper too, because this may be more interesting than the 3D stacked memory. I don't know. How many people know this paper?
It's a book.
Oh, yeah, book, sorry, yeah, it's a book, exactly, it's a book. Oh, you don't? Okay. So if you have taken a performance modeling course or scheduling theory, you might have studied this, basically. I think it's a very good book, very seminal book. But I'm going to point out one thing in this book. This is called Decision Makers Games. And I really like this section. You can go into rat holes in a lot of discussion. And if you look at this picture, these are the rat holes that show workload is a big rat hole, metrics, configuration, and detail. Basically, Rod Jane says, even if the performance analysis is correctly done and presented, it may not be enough to persuade your audience, the decision makers, to follow your recommendations. The list shown in box in the next page is a compilation of reasons for rejection heard at various performance analysis presentations. You can use the list by presenting it immediately and pointing out that the reason for rejection is not new and the analysis deserves more consideration. I think of this as science in the end. A paper is not the end of the world. It requires more consideration going into the future. Also, the list is helpful in getting the competing proposal rejected. No, I don't recommend using it for that purpose. Okay. Anyway, I like this basically. Reasons for not accepting the results of an analysis. This needs more analysis. And the last one is very nice, I think. Why change? It's working okay. I think that's exactly where we are in how we deal with computers. We're designing systems that are working okay. No problem, actually, right? We don't need to really improve them. Except we have a huge energy and sustainability problem, in my opinion. And this is, we've heard this also. I think the first, when people were working on high-performance processors in the 1980s, some people were saying, why improve the performance? Anything better than, we don't want anything better than MIPS R2000, because that's the best processor we can have, right? But clearly that's not true, right? Okay. Okay, anyway. Yes, please.
Do people ever mention von Neumann architecture?
In what?
In general, because this is not it. And
you mean Ambit is not it?
Von Neumann architecture.
Uh-huh.
The whole thing is not it.
Yes, that's right. Uh-huh.
Is it even a point?
In their use, you mean, or
in the criticism?
No, that was not a point at all. Yeah, that was not mentioned.
So if you tossed it out the window and don't even mention that name, and this is how it should do computation, your experience, you haven't been questioned.
In terms of, yeah, that's not, I don't think that's a point of contention for most people. Most people understand the downsides of that bottleneck, von Neumann bottleneck. We can talk more about it. Okay. Now that I've detoured a little bit, let's pull back. I have a lot of stories if you're interested. So we're talking about memory as an accelerator, and we're still thinking of memory as an accelerator. Now we're going to talk about 3D stacked memory a little bit. So this is actually even more opportunistic, let's say, because 3D stacked logic and memory device already exist. Hybrid memory cube is one example. High bandwidth memory is 3D stack capable. Basically, you have logic underneath a logic layer underneath memory layers, and logic layer is connected with high bandwidth, low latency connections to the memory. And there are even more true three-dimensional technologies that are under development. What do I mean by true? That means that instead of the through silicon vias that go across all of the layers, you have vias that connect adjacent layers. And these vias can be much denser than the true silicon vias. Like the next architecture from Stanford is one example for this. So these 3D stacked memories exist, and this was the Ramelator paper that I mentioned earlier. Even at that time, we had a bunch of 3D stack capable memories, and more are going to come up. And we wanted to really understand what can you do with these memories. And whenever you have this sort of technology, it's always good to ask the question, what is the maximum thing that you can do, and what is the minimum thing that you can do? And we wanted to cover the entire space as much as possible. And I'm going to give you some examples of the research. So what is the maximum thing you can do? What does that mean, basically? If you had the possibility to change the entire system, going from the programming model to the compiler to everything, basically, and the hardware, what would you do if you had 3D stacked memory as a building block? And we're going to use it as a coarse grain accelerator. I'm going to talk about that. Next level, maybe you don't have the possibility to change the entire system, but you can do some simple function offloading. You identify your functions in your workload, and you offload them to the logic layer. What are the things that you should offload? And on the opposite end of the spectrum, basically, what is the minimal processing and memory support you can provide with minimal changes to the system and programming? This is very different from this. So let's start with the first one over here, because it sets the limits. And what I'm going to describe is work initially. This changing the entire system work is actually work from 2013, 14, 15. I give this range because this paper got rejected a couple of times also. But later, actually, people improved this work, and the numbers are much better, basically. Other people, not us. They actually improved the way you do the data mapping, data partitioning, graph partitioning, etc. And you can actually get to speed-ups much larger than what I'm going to describe over here. And I'm going to tell you the speed-ups that they have also. Okay, so at that time, when we first started looking into this, we said graph processing is a really interesting workload, and we should really accelerate it. And it's a good fit for main memory, in-memory processing. Because it clearly is over there. It clearly is in many social networks. Bioinformatics is moving a lot into graph processing. A lot of machine learning frameworks are based on graph processing. And scalable graph processing is challenging because if you throw cores at the problem, you don't get a lot of benefit. Because a lot of what you have is bandwidth bound. Basically, it's not all of it, but a lot of it. Basically, a lot of the core kernels have frequent random memory accesses and with little amount of computation. They're really exercising this energy cost and the data movement cost that we discussed earlier. So what did we do? I'm not going to go through this. It's a full system level paper. We didn't go and design the hardware, of course. We stopped at the simulation over here. But what we have is these 3D stacked logic and memory. And if you look inside it, basically we have a distributed accelerator that can do graph processing. This accelerator is interfaced similar to a GPU today. It's non-cacheable, physically addressed, it's memory mapped. Basically, you offload your graph computation to it, and graph computation happens, and hopefully happens fast and efficiently. So what does this accelerator look like? It's an interconnected set of these 3D stacked memory plus logic units. Let's call them cubes. Let's say cube. And essentially, in each cube, in the logic layer, you have a vault. This vault basically operates on the memory layers on top of it. So basically, the thing is partitioned in the vaults, and each vault has some memory associated with it. Each vault has essentially a DRAM controller over here, and we add an in-order core into this vault. Very simple in-order core. The reason we add very simple cores is because we're bound by thermal constraints that we have in the logic layer in the cube itself. So we cannot add very complicated logic. There's also area constraints. But we have a lot of analysis of this in the next paper that I will briefly mention. So basically, what these vaults are, each in-order core can operate only on the memory on top of it and the values that are sent to it. And they can communicate with the other vaults inside the same cube. And they can communicate with other cubes or other vaults inside other cubes. So the way the communications are done are by using remote function calls. Essentially, this is a distributed system that you have. Whenever you want to, somebody partitions the graph, and this is very important. If you partition your graph to maximize locality, that's great. Basically, you partition your graph, and if you want to operate on a graph node, you need to send a message to the vault that houses that node. Since everything is physically addressed, the programmer knows all of the addresses. Of course, programming is not easy, but it's doable. Meaning that data doesn't move. Well, the intermediate values move, but the graph nodes don't move. So you basically update the graph nodes by sending messages to the graph nodes. That's the idea. So the programming model is very similar to send and receive based programming models that you have in distributed systems. It's message passing in the end. Okay, what else do I want to say? So the cores can communicate with each other. There's some sort of network inside this. And there's some sort of other network over here. We had a dragonfly over here. But of course, I think networking is really important over here also. And we have some support for communication, as you can see. Okay. Okay, I guess I'm going to not talk about this one as much, but basically it's a put and get based programming model. And you can see there are some barriers over here. Okay, we also had some prefetching mechanisms over here into the vault, because it turns out the simple in-order cores cannot saturate the huge amount of memory bandwidth that they get exposed to. So we had prefetching. Some of them are locality-based prefetching and message-triggered prefetching. The paper has more detail. So let me give you some results. There's a lot more detail, of course, on how the system is designed. But let's take a look at the performance. So this is a DDR3-based system, which was the state-of-the-art at the time. It's 100 gigabytes per second. Hybrid memory cube. It's exposed a different interface to the cores, but compute memory dichotomy is still there, as you can see, but it has a higher bandwidth. And this is out-of-order cores. This is in-order cores. I'm not going to talk about that as much. The reason we have in-order cores as one of the baselines is because we will have only in-order cores in Tesseract. So we call this Tesseract because Tesseract is a three-dimensional hypercube. If you look at this, Tesseract is very different, clearly, because the compute and memory dichotomy is not there anymore. You cannot separate them from each other. And you get 8 terabytes per second exposed to all of the cores, all of the 512 in-order cores that you have over here. And this is the performance improvement that we get on 5 graph processing algorithms. This is the average performance improvement. Basically, including the prefetching mechanism, we improve performance by about 13.8x compared to DDR3, which is significant, but we changed the entire system also. And we didn't really optimize the system. Later, people actually developed data partitioning algorithms and also better scheduling algorithms. We had a lot of inefficiencies in parts of the system also. They improved that also. They're actually a sequence of papers written by multiple groups on top of this. And I think they've improved the performance to more than 2 orders of magnitude right now. It's about maybe 150x if you actually include all of them. So I think the potential is actually there. Okay, so in our system, actually, the benefits is, part of the benefit is clearly coming from, we're able to exploit the bandwidth that is exposed to these cores. And we have a lot of analysis. Where is the benefit coming from, actually? But you can see that we have 2.9 terabytes per second out of 8 terabytes per second that's exploited. We're not as efficient as the baseline system. So that tells you that we could actually do even more over here. Okay, there's more analysis in the paper. There's basically benefit coming from just bandwidth, benefit coming from the programming model, and the paper has even more analysis than this. But it's not just because we're throwing bandwidth at the cores. You really need to change the programming model as well to take advantage of it.
So just a quick question.
Yeah.
In terms of security, do you have any mechanism that can, like, you can do memory protection, hypervisor, this kind of thing?
On this one? No, nothing.
So you also need to expose some mechanisms to forbid, like copying row that you don't have access to and these kind of things, right?
In this case, you mean?
Yeah.
Well, in this case, we basically have only one application, and we assume that the entire accelerator is dedicated for that. Yeah, that's the assumption, basically. We're not doing multi-programming or anything. But yes, if you want to make it...
The same problem applies to row clone as well, in a sense.
Yeah, but row clone is simpler because row clone, the processor controls it. The processor says, copy this row to another, so all of the checks must happen over there. Here, if you want to add checks, you need to add... Basically, it's a very vanilla, very early GPU type of accelerator, let's say. Early GPUs were kind of like this. They were completely physically addressed, non-cacheable, not many security mechanisms. Yes?
the partitioning actually imply in terms of the performance?
Yeah, so graph partitioning, right? So that's actually a very major thing. So basically in the paper we show that if you do the partitioning better, you can get even better performance, but you need to be very careful. So later works, they got a lot of benefit by doing the partitioning in a much better way.
And if you change the workload, you change the partitioning, I guess? Or?
Yeah, you will need to, exactly. Yeah, exactly. Actually, in our paper, we show that if you use the same partitioning mechanism for all of the workloads, sometimes your performance degrades because that partitioning mechanism is worse than the baseline partitioning mechanism for that workload. Yes?
And the partitioning has to do with the 3D aspect of it.
So it has to do with both the 3D aspect of memory and also, basically it's a distributed system. You want to keep the communication as local as possible. And also within you want to keep the communication as local to a vault as possible. And if you cannot do that, as local to a cube as possible.
But if you look at the pseudocode that you change, the 3D is performing the inner loop for you?
Yes. Yes, exactly. Okay, so energy improvement is also significant. In our case, we show that it's 8x, but again, later works show that you could get close to maybe 80x or so. This is system level energy. This is full application. Okay, but that requires clearly changing the entire system actually. And I think some people, once you have 3D stacked memory, some people will do this. This is exactly how GPUs came into being powerful compute engines, right? Some people said, okay, we can use this compute engine for something else. And they started putting effort into it, and they actually put a lot of effort into it. And now GPUs are actually becoming much more general purpose over time. I believe the adoption can go that way also. Once you have the capability to do some computation inside there, people will take advantage of it. I have no doubt about that. Even if you don't have programmability in an easy way. Okay, so let's take a look at more programmable or simpler ways of taking advantage of it. So we're going to talk about simple functional floating. And we did a lot of work in this area, but I'm going to talk about this work that we did with Google. So we spent about 1.5, 2 years together with Google to understand some of these workloads and characterize them. And we wanted to basically look at the data movement bottlenecks well, we narrowed it down to 4 workloads. These are the workloads. And the first observation we have is, as I mentioned earlier, average across all these workloads and interesting input sets, more than 60% of the total system energy is spent on data movement. And we wanted to understand the potential of processing in memory with 3D stacked memories again, just like the previous one, except we didn't want to change the entire system here. We have still the processor over here. Let's call it one Neumann model. It offloads functions to memory over here. But of course, the challenge in a mobile phone is you have very limited area and energy budget over here and power budget and thermal budget. So this becomes more stringent. So we have a lot of analysis of thermals over here, which I'm not going to talk about. But the second key observation is a significant fraction of the data movement often comes from very simple functions in these workloads. I'm going to give you some examples of this. And the observation is that the idea is that we can design lightweight logic to implement simple functions in memory. So you could design a small embedded low power core, simple in-order core like we discussed, or you could design small fixed function accelerators, and we looked at both options. Clearly fixed function accelerators perform better, but they're more specialized, they're more effort. And I think a good direction is really having both plus some reconfigurable logic so that you can actually reconfigure the logic to the function that you're doing in a particular workload. So the logic layer actually can accommodate a lot of that, in my opinion. So overall, the performance and energy benefits are about 2x, let's say. This is written in a different way. If I were writing the paper again, I would say about 2x or so, or whatever that number is, if you divide this by 1. So it's not 13x, it's not 100x, and I don't think it's going to be a whole lot more than 2x in the end, but 2x is not that bad also. So let's look at some of these functions very quickly. I'll pick TensorFlow as an example. But if you have a neural network, you're doing inference, we basically analyze a lot of these applications in a similar way, but we found out that more than 50% of the inference energy is spent on data movement across many networks that are run on mobile systems. And more than 50% of the data movement actually comes from preparing the data, let's say. Packing, unpacking, and quantization of the data. And these are actually very good fits for processing in memory. Basically, packing or unpacking is reordering the elements of matrices to minimize cache misses for matrix multiplication so that you can do the operations better or with more locality. And this leads to significant energy and performance. And it's a very simple data reorganization process that requires simple arithmetic that is very good fit for doing it in the logic layer. Quantization is similarly, because actually all networks do this, you don't use large floating point numbers, you use simple integers to reduce energy. But while you're doing the quantization, it takes time. You need to move the data to do the quantization, and it doesn't make sense to do it in the CPU. It makes a lot of sense to do it in the logic layer because you minimize the data moment. And it's a very simple data conversion operation again. It requires shift, addition, and multiplication, and you multiply it, and you can do it with lookup tables also. Okay, so these are two example functions, but there are other functions. So we examined the Chrome browser heavily, for example. Compression and decompression are clearly functions that you can offload to memory because they have a lot of data movement otherwise. There are a bunch of other things related to screen, and in terms of video playback and capture motion estimation is one example. But basically, it's very application specific. You need to go and analyze the applications, and this is what my student Amirali did over here. So that's the programmer burden over here to figure out what to offload. Okay, and of course, you need to design the accelerator if you're going to do it through the accelerator. And there's a lot of benefit to accelerator. So if you do it with a general purpose core, you don't get a lot of performance, but if you do it with an accelerator, you get a lot more performance in some of these functions, as you can see. Okay. Any questions? Okay, I'll keep going since we don't have a lot of time, I guess. You had a question? 20 minutes, okay. That sounds good. I'll cover 500 slides in 20 minutes. I'm just kidding. Yes?
It's a different question.
Yeah.
Could you do the same kind of, let's say, computation in a cache instead of in the DRAM?
Yeah. So,
do you know of some work in this direction?
You mean the 3D stack computation, or?
Whatever.
So actually,
yeah. Some computing units in the cache itself.
So there's definitely some work in that direction. You can find actually the Ambit idea, the triple row activation, that's also exploited. It's called compute caches. That was published recently.
Have different DRAM chips that would just
send data over there, and then basically you can aggregate the data inside the cache. And there are reasons for doing it inside the cache as you. So the ideas that I mentioned earlier are applicable to caches also. No question about that. I think a good research topic is figuring out where to do what and how to aggregate the data when you need to do it actually. Okay, so we've been looking a lot into GPUs also. I'm going to give you some more examples very quickly. But you can, for example, have a very sophisticated GPU, main GPU, and you can offload functions to simple GPUs that are in the logic layer because simple GPUs cannot be sophisticated over there. And here, especially if you have a distributed memory that looks like this or NUMA that looks like this, then you have a problem, right? Meaning, if you're adding A, B, and C, and if A is here, B is here, and C is supposed to be there, it doesn't work to offload the computation. So we looked at data mapping mechanisms as well as offloading mechanisms. This particular paper actually does it completely transparently to the programmer. We developed compiler passes to figure out which functions in a GPU program should be offloaded to these small GPUs near memory. And we also did the data mapping. There's a heuristic that does the data mapping in a nice way. Again, completely transparently to the programmer. Programmer doesn't do the data mapping. We use some heuristics to decide which data should be located where based on the operations that you perform on the arrays in some of these programs. And you can use some heuristics to do that. And in the end, the performance benefits that you get over here are about 30 to 50%. So it's not even 2x over here. So we're going down and down, as you can see. This is completely transparent to the programmer. It's not bad, but it's not 2x or 13x or 14x. Okay, I'm just going to skip some of these. Clearly, you can accelerate pointer chasing in 3D stacked memory. This actually improves the latency of pointer chasing significantly. I'd be happy to talk about that separately. You can do things inside the memory control without having 3D stacked memory, and I think this also improves, especially pointer chasing type of operations. When you have dependent cache misses, offloading things to the memory controller helps a lot. And we see significant benefits over here. Again, significant meaning it's not 2x, it's not 4x, it's not 13x. It's about 20 to 50%. Because, again, this is also completely transparent. Once you have an intelligent memory control, you can do other things like prefetching. Again, I'd be happy to talk about it. I think the opportunities are actually endless. But let me go into this last part over here. Basically, what is the minimal thing that you can do? Because this ties into the adoption issues. If you really want to adopt these things in the masses, you really want to have a path for it. And I think that was the question we asked also. What can we do minimally with minimal change to the system and programming? And I'm going to talk about this very briefly. And the idea is very simple, basically. Well, we want to have minimal cost, minimal changes to the system, no changes to the programming model, no changes to virtual memory, minimal changes to cache coherence, almost no changes. So the key idea is very simple. Basically, you expose a PIM operation as a cache coherent virtually addressed host processor instruction. So you add an instruction called PIM-enabled instructions. And you restrict it to operate on a single cache block. Because whenever you operate on multiple cache blocks, problems appear. You need to translate multiple things. You need to protect multiple things. You need to ensure that coherence is maintained across multiple things. But if you operate on, and you need to map multiple things to the same place. Whereas here, if you operate on a single cache block, that cache block is mapped in a single memory module, and you fix all of those problems. And the translation is not really across different cache blocks. Okay, so a basic idea is this. You have a PIM add instruction that looks like this. No change to sequential execution, no change to virtual memory, minimal change to coherence so that you ensure that nobody else is updating this block while you're updating it. No need for data mapping again. And the second key idea is, of course, once you have these operations, you have a choice. Where do you execute this operation? Do you execute it in memory, in the logic layer, or do you execute it inside the processor? Because the processor is also capable of executing it. And we have a mechanism to predict, simply to decide that. Okay, so let me give you an example over here. Again, this is PageRank as an example. In the baseline, you have to communicate a lot. So you have to get a single cache line in and a single cache line out. Whereas if you convert this to a PIM add, you basically need to send only 8 bytes over here to the update, assuming the value is 8 bytes. So you can basically reduce the bandwidth requirements by 16x. Okay. So of course, always executing in memory is not a good idea. It depends on the size and caching effectiveness, size of your cache and effectiveness of your caching. If you always execute in memory with the operations that we've identified are as good, which is also an interesting research problem. What operations should be PIM-enabled operations, right? But with the operations that we have identified, you sometimes lose performance and sometimes gain a lot of performance. Well, a lot, you can see the scale, right? So when caching is very effective, you don't want to offload to memory. So these are the instructions, basically. Based on our workloads, these are the instructions that we decide. For example, dot product is an instruction that's used for machine learning, Euclidean distance for streaming analytics, histogram binning, hash table probing for hash joins, floating point addition. These are the instructions that we ended up having. Again, this is based on our students' imagination and us. There could be more over here. Having a configurable instruction set, I think, is a good idea also going forward. A more open instruction set so that you can take advantage of the ability to add instructions. Okay, I've already said a bunch of things. I'm not going to talk about the P fences over there, but it's very similar to the memory fences that we have today.
It's not a persistent fence.
It's not what? No, it's not a persistent fence. This is our PIM.
Overused.
Yeah, exactly. This is PIM fence. Processing in memory fence. Basically, it ensures that all of the operations that are sent to memory should complete before you move on to do any operation. Okay, so this is the key to practicality. You have a single cache block restriction. Of course, this makes things more practical, but this also reduces the benefit. Ambit operates on huge amounts of data, right? 8 kilobytes or more, but this one operates on a single cache block. Okay, I'm going to skip that. So basically, these are the results that we have. We have 10 workloads, interesting workloads, hopefully. We could always have more workloads. Remember the rat hole, the big one? That's the workload. But basically, we get about 47% average speed up with large input data sets. With small input data sets, we can still get some speed up and significant energy reduction, 25%. So again, it's not 13x, but it's reasonable. And I think handling small and medium data sets are important because, for example, here, small data sets, if you don't handle them well, if you ship things to memory, you lose performance pretty much all the time. But if you handle things well, you decide not to ship things to memory, basically you don't lose performance. And medium data sets is where you actually gain performance significantly as opposed to losing or not gaining. These are places where you don't know how good is caching. And clearly our algorithms are not great in the sense that sometimes we lose performance compared to shipping everything to memory, right? Which means that we're making the wrong decisions. So there's room for improvement over here. And this is the energy consumption. With large input data sets, you get about 25% per node energy consumption. Okay, I think some of these are obvious, but so the granularity is an issue over here, basically. I think this doesn't take advantage of full PIM potential, single cache block. In terms of the data granularity, there's a problem. In terms of the function granularity, there's also a problem in my opinion, because you're limited to single instruction. Yes, you can make the single instruction arbitrarily complex potentially, like we've done with the dot product, right? But dot product is just one function. You can actually perhaps increase the granularity of this and take advantage of things more. And we have some work that is in the works right now that shows that if you select a better granularity, even with the single cache block restriction, you can actually improve performance even more. Okay. So as I mentioned, we talked about automatic code and data mapping. So basically, we need some more automatic mechanisms also. So adoption, maybe we should talk about this a little bit. Because whenever you have a paradigm change like this, you really need to think about adoption, I think. Actually, one of my favorite keynotes that I've ever attended was at ISCA in 2005. Do people know the name Arvind here? Arvind from MIT. He gave the keynote at that time. And it was a very eye-opening keynote for me as a PhD student. I was a PhD student at that time. And what he said was, he, of course, described data flow. They did a lot of work on data flow. And he said, we made one mistake in data flow. We focused too much on hardware. Meaning they should have focused on software to enable the adoption. And I think that's true for whenever you do any kind of hardware change. If you focus too much on hardware, you're not going to get adoption as much. And all of the issues that I have over here, I think, related to software in the end, at some level. So what is the functionality of an applications and software for PIM? I think that's really important. That's why we've been examining. Actually, right now we have about maybe 400 workloads or so that we have mapped to different types of processing in memory architectures. It's very interesting to examine different workloads, I think, and I'd be open to other workloads as well. Ease of programming, as we mentioned earlier. How do you actually ease this, make the interfaces easier, add compiler and hardware support to enable the programmer to take advantage of it better. System support, coherence, and virtual memory. I think these are the most hairy parts, perhaps. Programming, at some point, you need to pay the cost, but virtual memory actually is one of perhaps the hairiest part. Coherence, I think we can solve. But virtual memory, if you want to do the translation, you cannot get away without doing the translation somewhere, right? And we have some mechanisms. We have a paper that talks about virtual memory, but I think the solutions are not going to be easy. I think people really need to rethink virtual memory going forward with the huge memory spaces, with the huge storage spaces that we have. Maybe we should really not burden the systems and the hardware, software and the hardware too much with virtual memory. We should probably think about different approaches to address translation going forward. Do you agree? Okay. Because I'm not sure if there will be a good solution. I would recommend looking into this, but this is a very hairy issue, I think. Coherence is interesting. I'll briefly talk about that. So on top of, basically we want system support for this. We also want other types of system support, maybe runtime and compilation systems for adaptive scheduling, deciding what to execute where, or at least helping the programmer to decide. I don't think programmer is the only one to make the decisions, because if you actually have a dynamic general purpose system where you have multiple programs, at some point, programmer may not be able to have access to everything that you have in the system, right? At least in a given time. So you need to have access and sharing control, like security that you mentioned. Data mapping is important, of course. And on top of this, we need to have infrastructures to assess benefits and feasibility, which is, again, a lot of software development problem. I think all can be solved with a change of mindset. Basically, we need to start somewhere. In the end, we will need to revisit the entire stack to answer all of these questions. But if we don't start anywhere, we will never be able to revisit the entire stack. That's why I like the idea of row clone, for example, because row clone exists. If actually someone makes it available, and I think you can do it in existing DRAM chips, you can write software for it, and you can start somewhere to actually take advantage of processing in memory, right? Okay, it's data movement in memory, but in the end, it's a data movement problem. I don't want to call it even processing in memory. It's minimizing data movement. Okay, basically we can get there step by step. So if you're interested, we've written these invited papers that talk about some of the issues. And this is a more workload, this is a more recent one that is more workload and programming driven perspective. So we talk a lot about workloads and outstanding issues over here. Okay, I'm going to go through this relatively quickly. So these are some things that we've tackled in terms of making things easier. Like this is a mechanism that automatically finds out dependent cache misses and offloads them to the memory controller. It's easy on the software programmer. It's extremely hard on the hardware designer, just like any software microarchitecture trade-offs, right? I don't think this is the best way of doing things, but it's very interesting to examine things. Okay, so this is the coherence part. So we've been looking at coherence a lot. We've been partitioning applications between the CPU and the PIM engines, let's say CPU cores and PIM cores. And it turns out traditional coherence mechanisms don't do too well. This fine-grained, like MESI coherence, coarse-grained, you basically have coarse-grained locks. And non-cacheable, clearly not a good idea. But sometimes you may want to consider it if you offload a lot to processing in memory. But basically, existing coherence mechanisms don't come close to the ideal coherence mechanism. So we have some mechanisms to actually come close, but I think there needs to be more work done over here. So the idea is to make things a little bit more transactional. You offload some code, and this is the more mature version of the work we called Conda. You offload some function to memory, and while the memory is executing, it keeps track of what it's reading and writing, and the CPU also keeps track of what it's reading and writing. And periodically, or at the end of some boundaries, function boundaries, you basically compare the signatures and decide whether you roll back the processing in memory engine and restart. We never roll back the CPU over here so that we're compatible with many different types of memories. But we roll back the processing in memory engine. So I think this is, as far as I know, this is the first work on processing in memory, coherence between CPU and processing in memory. But I think to be adoptable, this requires even less overhead. Because there are really cases where you want to partition your applications between processor and memory. For example, if you're scanning, if you're doing analytical queries on your database, that's a very good fit for processing inside memory. But if you're doing transactional, that's a very good fit for CPUs. And if you partition them, the problem is how do you keep things coherent? Okay, as I said, this talks about virtual memory a little bit, but I'm not completely happy with the solution in the sense that basically we carve out an area in memory where the translation is done inside the memory, and the CPU doesn't have any power over there. So you memory map a region where the translation is completely under the control of the processing in memory engine. I think it's a good step, but it really partitions your virtual address space in the end between the processor and memory. And as far as I know, I don't know of any way of getting rid of the doing this efficiently without partitioning the virtual memory address space somehow. Because if you don't partition the virtual memory address space, you have to have the same translation tables on both places, right? And you need to keep that coherent also. So I think virtual memory is hairy. Okay, you can also think about data structures, which is also interesting, I think, but I'm not going to talk about that. Okay. I'm going to skip some of these slides, since we only have 7 minutes, right? Okay, maybe I'm going to skip this one also. I can finish earlier. I don't want to finish earlier. I want to take questions if people have questions. Any questions? Yes, please, sir.
It's about algorithms. So if I think of the classical algorithm, you already mentioned it, you look at computation, that's it. What would the computation model have to look like that covers what you have presented? Are there any approaches? In the sense that you can set an algorithm and analyze it in a way that gives you some of your ideas?
Yeah, I see. Basically, is there a general approach to?
Are people working on that?
Yeah, I'm not sure. I'm not sure if we have enough information, enough understanding of the processing in memory systems today to answer the question that you posed. I think it's a very good question.
It looks a bit like communication complexity plays a role, and then you have very distributed algorithms.
Exactly, yeah.
I'm just wondering.
Yeah. I think I've seen some work on analyzing the data movement in algorithms, but I'm not sure if there's enough understanding that enables an answer to your question at the moment.
Because it's really very different from what you normally think.
Exactly. So I think for ambit-like algorithms, the vertical data processing systems that I mentioned, there is some theory that was developed in 1960s on that topic. I'd be happy to share the works. This is by Schumann. They actually called vertical processing systems. It's very interesting. I think it's very early, ahead of its time. But I'm not sure about this other type, like general data movement I'm not sure about that one.
Thanks.
Yeah, you're welcome. Yeah.
Maybe my question is actually connected to what you just said.
Okay.
I'm curious of this three rows activation system
Sure.
that does essentially only bitwise operations, right?
Sure.
So what about the word operation?
Yeah.
If you say something and I missed it.
Yeah. No, I mean these don't support word operations at the moment.
Because there are ways to do it, right? One
Yeah.
is one way. I can think of at least two things. One is to do shifts in a row.
Exactly.
Which
Yeah.
is very easy to do, probably, right? Because the whole buffer is just
Yeah.
a small modification. And then I think as soon as you can do a shift of even one bit, you can start.
Yeah. So I agree. So shifts, we actually have some work that's ongoing. With one bit shifts are easy. If you start going 2 bits, 3 bits, then it becomes complicated. Clearly, you build a shifter across. But yeah, 1 bit is a good start. I agree. Yes.
And the other thing is actually to project things completely differently. Like you take nanny synthesis algorithms, they synthesize in majority functions, and then you scale the data flow graph, and you use this as a 32,000 vector processor.
Exactly. Yeah. Exactly. Exactly. I think those are a very good fit for this sort of systems. Yeah, but generalizing it is a very good research direction. No question about that.
Yeah, that is easy to generalize.
Yeah.
This form is, the question is, do you have applications where you need 32,000 vectors?
Yeah. I think some of the databases are there actually. The bit funnel is also, yeah.
So how do you compare this in-memory processing with all the efforts also done to have computation on the disks, on the SSD, and where latency is even higher?
Yeah. So I think these are complementary. As I mentioned earlier, we should really enable computation on all of those components. No question about that. If it makes sense to do it in the disk, I think I'm all for doing it in the disk.
Another question is, should we think of new kind of primitives or new kind of data structures that can be optimized for this kind of settings? So, for instance, we know the composite operation, the verify write operation. We have just a few of them. They are very simple.
Yeah.
But can we think of some different ones that are
Sure.
optimized for this kind of settings? And should we also change the way of designing data structures?
Yeah, absolutely. I think I definitely agree with that. We have not done a lot of work in that area, and I haven't seen a lot of work in that area. But I think we should think about different way of designing our data structures. Yeah, and algorithms also.
Good research ideas.
Yeah, exactly. I think there are research ideas all across the stack, in my opinion. Okay, maybe I'll present something else then.